developing a polynomial relationship so that for a number of replicate samples that you send through, you can get the standard deviation of your blank, which the College of American Pathologists simply doesn't do. And then this would be the coefficient of variation there. This is another coefficient times the square of the concentration and another one times the cube. But from this, you can develop a good estimate of the deviation with which any serum level is measured that goes through your lab, so that you can then fit it correctly according to its credibility. Store it in the software, and there is no need to censor low data anymore. There is no lower limit of quantification. That is an illusion that comes from the laboratories using coefficient of variation as their erroneous of laboratory precision. Here's an example. Here's our hospital's gentamicin assay. And here we see the standard deviation of the assay over this range. Here we see the coefficient of variation. Here we see two samples that are measured with essentially identical precision. And yet one has a CV percent that is twice that of the other, simply because the measurement is half of it, both measured with. That's where that whole idea breaks down. And what is wrong with the laboratory community, I do not know. But they will die rather than change. And I've sent them manuscripts, which they just rejected because they don't want this to their readers. And maybe it's not, but it is to me, and it's coming out now. Now, we need to track renal function in acutely ill people. Cockcroft-Gault and other methods of estimating clearance without a urine specimen will not do this well for patients acutely ill with changing renal function, because you can't do it from just one serum creatinine. You need a pair. And you need, what is the creatinine clearance that will make my patient's serum creatinine go from this first level to this second level in this time period in a patient of this age, sex, height, and weight. And doing this, you can do as well as the standard 24-hour urine collection in a research setting. And the evidence for that is here, because we're the only people I know that have asked the question, what are the errors of the classical research determination of creatinine clearance? Well, usually serum creatinine can be measured with a CV of 5%, a urine with 8%. Then if you can collect a 24-hour urine with a CV of 5%, you add the variances and take the square root, and the classical creatinine clearance has a variation of 11%. So that's 95% confidence limits of plus or minus 22%. And that's the classical gold standard that nobody ever asked us about. Now, how well do we do? This is from our renal transplant unit, where we used this. Kidney took hold and serum creatinine, renal function improving, and we see this correlation between the measured and the estimated, and the scatter in this is just about plus or minus 2 standard deviations. So in this way, without a urine specimen, even in acutely ill patients, estimates of creatinine clearance that are as good as the classical 24-hour collected urine gold standard. Now, we come to optimal protocols for monitoring, for getting serum levels, and this is a really neglected area in the therapeutic drug monitoring community. But don't wait for a steady state. Start right in with the very first dose. Never leave your patient at risk by not learning how the drug is behaving, so that you can make your adjustments just as soon as possible. It's nice to get one sample for each model parameter to be estimated. And D-optimal designs have been around a long time. And one good strategy is to get a peak and then a sample when you think the levels are about 1/3 the peak, as a rule of thumb. Don't waste your money with poor design. Start right now and use at least D-optimal strategies. Dave Bayard, here we see, if you ask at what time does a change in the volume of distribution make the biggest change in the serum concentrations, if the volume of distribution were 10%, then all these others would change by 10%, and the biggest change would be the peak. That's why this is the best time to get a sample to understand the volume of distribution of the drug. If you want to look at the elimination rate constant, get a sample when it's down to 36%, or about 1/3 of the peak. And there are sound reasons behind this that we can go into if you wish.